Yeah, okay. Wow. All right, generating functions. So good. These guys. Yeah, so we just derived, well, we didn't get it right? We did get it right for Poisson, but it was wrong. So we're gonna we're gonna use the approach of generating functions to find out all sorts of things about these random networks. Very nice. And so this is, combinatorics world. Lots of beautiful things, quirky, fun things that matter too. So we're gonna do this. I will give you a piece later on that gives you a much more sort of physics kind of transparent explanation for a lot of these things as well, which took some thinking to get to. But generating functions like Fourier transforms, Laplace transforms, these other kind where you move into some of the space, sort of weird magical space in some ways, and you can do all sorts of things there and you come back into the real world. So there's a bit of, it's got that kind of flavor, but it's discrete. So we take discrete things and turn them into continuous things that we can play with, which is kind of an odd thing to do, and then find out something about our discrete guy, right? So, in its simplest, it's really this. So you have some sequence of numbers, or things, right? It could be things, but just numbers. And we're going to attach them to mathematical objects that are distinguishable, right? So for Fourier, there are very good reasons for doing for Fourier, but Fourier, you think these things are orthogonal to each other, right? These waves are orthogonal to each other. Say for, you get more complicated things, more complicated kind of orthogonal functions, all sorts of things, depending on the problem you're solving. Wavelets, for example, right? Really good things for images. Okay. But we'll choose a very, very simple one. So we can play around with these numbers in odd ways. So generating function, the combinatorics world, you see some versions of this in statistics as well, with different names. So we'll just be this, right? So we have A0, A1, A2, and we'll multiply A0 by x to the 0, so just 1. A1 will be multiplied by x, right? So it's just a polynomial story, right? So if we were doing Fourier, we could put x, replace that with e to the I omega. They're all adjacent. Laplace is e to the minus lambda. Okay. Yeah. Okay, so yeah, so it's a kind of a funny business. All right, so let's see. So we have a vector. It's just a vector in R infinity in principle. It just goes all the way down into some kind of function defined on R1, and then we can do magical things with that function, and then which is terrific. It's very much a math kind of thing. Like so. We'll kind of run around in this weird landscape and then jump back out to reality and say, hey, look what we found. But it's so very powerful, but it doesn't mean you're always doing something that's intuitive or, your path to get there. So, it's like doing a real integral using complex, using an integral in a complex plane. It's insane. Math is full of dirty tricks, basically. All right, so okay, so talked about these other guys. So here's a simple one. We'll be talking about probability generating functions, right? So this is the very general thing. And by the way, so I guess I cite this, but Wilf, WILF wrote the great book on generating. So it's called Generating Functionology, and it's really cool. So there's free versions online from older editions. I think he may have. Yeah, he got to the 3rd edition, I think. Yeah. Anyway, it's beautiful. It's a lot of fun. It's about getting a black belt in generating functions. It's written like that. All right, so imagine you just have, so a probability one. So imagine you have, you're rolling a die, right? And so we'll assign 1 pip to x to the 0 and 2 pips to x to the 1, right? We'll say that's what they are. And so these are simple, so we know it's 1/6. The probability is a 6 for each one. And so we end up with this. And in fact, all right, okay, sorry, right. So we're actually going to say for getting k equals 1, 2, 3, 4, up to 6. Makes sense. Because that's the realized value, right? That actually matters, yeah, realized value. So this is x to the 1. So it'll be a 6 times x to the 1, blah, blah, blah. So we get this function. So now this is a function of x. We can play around with this in different ways. A coin, and I'll fix up those. That's what I was editing. It's ridiculous. I was just fixing because /rm doesn't work with this thing. You need text normal. Madness. All right. Right, you can't have this font. It's horrible to look at. Okay, so probably for a coin is, you get a head as a half and so on. Very simple. So we could write it like this. We could say, it's a half times x to the 0 plus a half times x to the 1. So this encodes a flipping of a coin. Now flipping of a coin is a half times 1 plus x. That's completely sensible. This function, a half 1 plus x, is a coin. But we'll call getting a head, say, 0, right? Yeah. And getting a tail 1. So we'll assign them scores, right? So if you flipped a coin 6 times and you got a score of 0, that means you got 6 heads. So you want to turn it into some kind of number. All right, so probably generating functions, they have all sorts of properties. So we'll see if we can test out some of these things later on. This is kind of a fun-looking one. But the sort of thing we'll start doing is taking derivatives of these things, and that will actually have we'll have good reason for doing it. Delicious properties, that's right. They really are. They're very, very nice. Okay. Yeah. All right, so here's another example. It's completely made up, but it's a degree distribution. It's got an exponential decay. And let me think about this. Okay. Is that right? So it's got some normalization, but e to the minus lambda k. So we're going to make the generating function for this guy. So k equals 0, 1, 2, 3. So it's exactly the right kind of structure we want. So it's c e to the minus lambda k, x to the k. So these guys group together. And, okay, let's think about that one. Right, we're going from we're summing something, we're going to turn it into a function of a continuous variable. So there's an extra step in there. So there's a c comes out, and it's really e to the minus lambda k. So it's e to the minus lambda x to the k. That's the piece that's in there. K equals 0 to infinity. These sort of structures that appear all, over and over again. It is a, yes. And so it starts with 1 plus, r plus r squared plus, so this is 1 over 1 minus this blob, because it's an infinite sum times c, like this. That's why the normalization looks like that. What's up? Sorry, say that again. Oh yeah, so we don't care about that.
Well, I'm studying for oral exams, so I'm just thinking.
We just doesn't matter.
I done all these tests.
We're not quite as worried about that. I mean, yes, a little bit, but not. Oh, no. No, but it is true. It is so true. Generating functions, you kind of you go a little berserk with them. Yeah.
Okay.
Yeah.
No, this is fine. I like it.
Yeah. Yeah. Some people have heart attacks. Okay, so there's a couple of nice things. So let's see. So if we evaluate it for x equals 1, right? So we put x equals 1 in there. That turns out to be very important. We put x equals 1. So this is 1 minus e to the minus lambda on the bottom. And c was 1 minus e to the minus lambda, right? In fact, because it's the same kind of thing, right? If the x was in here, we'd have 1 over 1 minus. We get, yeah. So it's equal to 1. So that should make sense. That's completely reasonable, and it's always true for these things because if it is a probability distribution that we're attaching to these x to the 0, x to the 1, x to the 2, if we're attaching it to these things, and we're adding them all up, when we set x equal to 1, well, we've got this, right? So it's a sum from k equals 0 to infinity, pk to the 1 to the k, so just 1. So it has to be normal. That has to be the sum of the the probability, so it has to be 1. So whatever, we'll make, we might have an f and a g. We'll have different generating functions making a third one, for example. That third one will have this property, even though it can be a little opaque to look at. You can certainly produce things where you can find the generating function for a sequence, but not the sequence. Right? That can be, you can get a nice closed form thing, but you can't undo it. This is true for, Laplace and Fourier sometimes, but you could then maybe you would do it numerically. So it's better than, nothing, right? Certainly much better than nothing. It gives you a handle on it, but you might very weirdly have the generating function for a sequence, but not easily write out what the sequence is. So that's of course true for these die and the coin PGFs, right? So they has to be true, right? So 1's in here, so we get 6 over 6. Yep. Plus 1, 2, right? So that's good. That's just a simple thing. Okay, good. Yes. You mean here? Nope. Nope. Here. Yeah. To get from here to here? Yeah. So the constant comes out, just C. And then this piece is really E, did I write this down? It's e to the minus lambda to the power of k, and then x to the power of k. Yeah. So this is... Oh, okay. So we don't care. Yeah, that's all right. It's okay. It's okay. We can always dial x so that that's okay. We can make x small enough for that to be true. Well, when we get to this function where we'll, so there is a radius of convergence, right? But then we can think it will blow up when x is 1 over e to the minus lambda, true. But we're happy to think about the function as being fine in general now. So yes, you can't do that. Like this sum explodes for numbers greater than 1. But once we've got it here, we're happy to think of it as, its continued version. It's like the minus 1/12 thing. Yeah, but so it's... Well, so this is given to you. This is the distribution. X we can choose. We can narrow x down. So we can narrow x down to make it happen, and then we can be like, oh, it's fine.
I'm just thinking because you pick x to be 1 there, and you say, okay, well that means that the sum of the probabilities is 1, which is good. So you would always, to me that says x should be less than 1. Always. Otherwise it should be. Like,
Yeah.
if you're going to be good about it.
Oh, no. You're all terribly worried. It's okay. Look, this is a device, really. So we're going to go out, play with these things, and then come back into the real world. Yeah?
I think it's so funny. You have to tell us, like, it's going to be okay. Like,
It's going to be okay. I like the concern. Nothing's going to explode. Well, if it does, we don't care. It's just some math. What could go wrong? Okay. So we okay? Sort of? All right. Well, let's keep going, and we'll see if your fear abates. The stress levels may just rise. Let's see. So, okay. So here's another nice little thing. Average degree. Okay. Average degree. This is it's very simple, right? It's k times pk. We sum over this. So let's see. We can manufacture that from generating functions by doing this. I'm just going to stick x to the k minus 1 there for no, typical kind of backwards argument here. And set x equal to 1. That's all right. Of course, I could put x to the n or x, x to the anything. Anything. Right? That's fine. But there's a reason for doing this because now it's introduced k x to the k minus 1. That structure, that's a nice little mathematical bit. Which is what? What do you want to do when you see that thing? You just want to race out there and do something with it. Yeah. It begs to be integrated, right? So this is really true. There are lots of, and I have to say, this is always a little game. Like if you have a guy that's sitting out here and it's kind of annoying you, there's a k, right, floating around, or k must do. Just put an x to the next power up or next power down, and integrate it and then and then differentiate it later on. You do all your stuff and then you differentiate it later on. Very, sneaky.
Is it how we don't care about the radius of convergence?
Well, we just don't care about it.
Otherwise, we'd have to be really careful.
My God, what have they done to you? We'll care if we need to. There's something. Wolf has a fun intro. I mean, it's fun, the whole thing. But there's something. I'm pretty sure there's a statement that he has in there about that would maybe help. Okay. What he says there. What? All right. Okay. So this is really nice. So now we can see this is really d by dx of x to the k. We'll pull the d by dx out. No one gets hurt. D by dx is out here. This evaluation is over here. This is now, it's pk to the x to k, and that's our generating function. So the average degree, or the average of whatever function, probability distribution we're dealing with, doesn't matter what it is the first derivative of the generating function evaluated at 1. So you could have, as I said, you could have a generating function which you can't really, unwrap and get back to a sequence, because it's just, it might look okay, it might be sort of benign. You couldn't, numerically you could kind of just get there, but you can always do this to find, say, a mean, and you can always do this to find do this kind of thing to find the second moment. So, okay, first derivative evaluate at 1, this will become our idea of what the mean is. Kind of weird. Right, so we're stepping away from reality, right? This is good, we're fine with this. Now, to find the mean of something, you differentiate it and evaluate it at 1. Completely sensible. Okay, so there are lots of nice calculations that you can do. They become simpler in some sense, but more abstract. So this is our derivative of our exponential, which I've done for you. Or for me, actually, because, yeah. So, right, I put the c in and so on. So this is c. Is sitting there. We had f of x was really this blob on the bottom. Yep. So you differentiate it, you get a -1 comes out. You differentiate this, you get another -1 for it, and you just get that e to the minus lambda on top, and there's a square on the bottom. Okay, that's the first derivative. We can set x equal to 1 here, and you'll see this will cancel with one of these. And we get this, right? So you can compute this, of course. You can do it this way, right? So we could go through and do it this way. But once you have the generating function, you take a derivative and you set it equal to 1. You don't have to do you're not doing a sum, right? You're acting on it. You're doing a continuous function thingamajig, calculus. So we allow calculus back in the room because that's kind of okay. Okay, so you guys can check for those guys if you want, right? So the average for for the coin flip, I made it 0 and 1, right? So the average should be a half. What was it? Half 1 plus x. So you take the derivative of this guy. So this is f of x. I want you to say it's opaque, right? At this point, so it's a half. It just is a half. Evaluate at 1, yes. Was a half. The other one is probably not as obvious, right? So f of x, when we had x plus x squared, there's a 6 out the front, plus x to the 6. So differentiate that. So we get a 6th, 1, ooh, this is hard, 2x plus 3x squared, plus 4x cubed, plus, that was lazy of me, but this is 5x, 4x to the 5. No. Wow, that was really bad. No, I just, what have I done? 2x, 4, 5. 5x to the 4 plus 6x to the 5. Okay, so it's doing the right thing. It's pulling down the number, right? So now evaluate this as x equals 1. You get 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is perfect. Divided by 6 gives you 3.5, right? So that's cool. Okay. But But yeah, so what's happening when you differentiate this guy, you're pulling the k down, right? So I sort of did it in a funny way, but you're pulling the k down. So if you differentiate again, you get k times k minus 1. Right? So if you want to quantify that, that would be good too. All right, so normalization, f of 1 is 1. First moment is this. Higher moments, we have to do something slightly sneaky, right? As I said, if you kept differentiating the generating function, you'd pull down a k every time. But let's look at this. So f of x equals pk x to the k. So first derivative, it's a sum. It's great. And we get k pk x to the k minus 1. So if we differentiate again, we get a k minus 1 coming down. Which if we wanted that, that's terrific. It's just a second derivative. But if we want to get another k to come down, we have to multiply by x first. All right, so we do that. So we say, okay, well, let's put an x in front of it. And now this is k again. And now we can differentiate that. So in fact, what it is this. Every time we do this, we get a k, it brings one k down and sets it up for another one. So if we do x d by dx n times, we're repairing this x to the k every time. Yes, this. Then that's the sum from k equals 0 to infinity. Every time it's come down, we've got k to the n, and we've repaired it, pk x to the k. So this is the nth moment. Cool, super cool. So we need this little operator guy here. Yeah. All right. So I was saying before, it's the generating function. You might have it, but it may be hard to extract the sequence. You can put it into Mathematica and get Mathematica to do things, and kind of hope that Wolfram is at the other end doing it for you, but he's not. So you could do this. If you think about this, this is going to work. So you take the kth derivative, evaluate at x equals 0, and divide by k factorial, and that will give you the kth element of your sequence, obviously, right? It's a Taylor expansion thing, yeah? So you've got these guys here. You've got pk, p0, x to the 0, plus p1, x to the 1, oops, plus pk, x to the k. So if you differentiate this k times, so let's do that, d by dx to the k, all of these guys go to 0, right? They get indexed down. And this one goes down to x to the 0. You get k, k minus 1, k minus 2. You get all those guys, so you'll get pk, k factorial. I don't like what I did there. You'll get k factorial times pk. All right, and this is all zeros this way. And the next one will be k plus 1 all the way down, but it will be, this one will come down to, it's 1 is going down, so this is x to the 1. Yeah, so it's okay. It's all the way down to 1. It really is this. Okay, but this, in some sense, 1 factorial on the bottom. And then the others are all powers of x. So when you set x equal to 0, all of these guys disappear. And you're just sitting there with x equal to 1. This is actually 1. So you've just got pk times k factorial. So if you divide by k factorial, you've got pk. So if you have a generating function that's a little messy and you can't expand it in a nice way, then you can do this. But derivatives get pretty nasty if you've got a few things on top of things.
So what does this mathematically represent, the generating function? So, I mean, I see
How it mechanically works.
we can get cool stuff out of it. And it works.
It represents insanity, actually. It represents monks climbing up walls and just doing crazy things in Europe, I have to say. I think so. And then just, and I mean, so it's more natural, say, in Fourier transforms. right? There is the wave representation. You can see why this shape can be made up of waves. You know, orchestra. You take out, an orchestra is a bunch of all these nice things, and you add it up, and you get some sound form, right? So that's there. This is more abstract than that. I mean, I have a couple of papers that say this is lovely, but it is, madness. So it doesn't. This won't make you understand. I don't think it won't make you understand processes necessarily, right? You still have to kind of, like, we can get results out. We can get out, say, conditions for giant components and so on. But there are other ways to get to those conditions that talk about the process much more clearly. Like, it tells you why, okay, it hits this node and that has so many friends and so, like, here's a story for it. Not so much of a story. But this is what math gives, right? So. We can talk about this much more, but I think it's yeah. So this is just a little painful, and turns out to really be fantastic. And powerful, right? So, yeah. Okay, so let's see if we can get this guy, right? So we had this condition just in the last set of slides, right? So it was the second moment minus the first moment divided by the first moment. This is for arbitrary degree distributions, otherwise random networks, right? Okay, so let's do it with generating functions because that's fun. So we'll find the generating function we'll just find it for this guy, take its first derivative, and set x equal to 1, right? So if we have that generating function, we want to find the mean of it, the mean of the distribution. We'll get the generating function and then do that. All right. Okay, notation. So this guy is going to be for P of k. If we have Q, we do that as well. So F of R is for this guy, right? So these two become the really crucial ones for understanding how things spread and how things fit together. This is what's going to happen, right? Once we've got the generating function, we just want the first derivative of this generating function to be greater than 1. Completely sensible, right? So we've explained why this bit is physical, right? This is a kind of as a physical explanation for this. This is a mathematical piece in the middle, right? This is sensible? Crazy. Okay. All right, and we can connect the generating functions together, which is nice. Yeah, that's cool. That's cool. All right, so in general, generating function, right? It's fine. This is the basic definition. We have rk x to the k, right? So this is the chance. This is the probability that your random friend has k other friends. So we put in the this formula that we created, right? So k plus 1 times pk plus 1 divided by the mean, which was this sneakiness over here. Okay, so we're sticking all this in here. So we're going to have to do some stuff with sums to get to our continuous function, but then we're good. Again, this bit of index shifting business. So this is an average degree. This is a constant on the bottom that comes out. We're going to put j equals k plus 1 here. We did this before. And that's going to tweak this guy, right? So k will be j minus 1. So that's happened, right? J, x to the j minus 1. Weird kind of funny things happen. I don't know what to say. It's just, yeah, we're just sort of pursuing this madness now, and we'll get some elegant statements out, which everyone is sort of thrilled with their charmingness in a way. But okay, but you have to be careful. But yeah, it takes a while to get a feel for these things. Okay, it's cool. All right, so we've got our PJ sitting here, and we see again, with great excitement, there's a derivative of x to the j. And then we'll sneak that guy out the front. And then we have the generating function for P. So we've gone from this generating function for R back to the generating function for P. There's one piece missing. Right, the first guy's not there. We had to be a little bit careful about that. Right, this was, we started at j equals 1, right? This started at k equals 0. We start really at j equals 1. If you put j equals 0 in there, it doesn't matter, right? It doesn't count. What happened?
Just pull the derivative out.
Man, you guys are just really... No. Which you do these things, and then 30 years later, a mathematician will say whether it was okay or not.
No, but here, I think like 100 years ago they put down in the book like,
I know, some bad things happen. This is totally fine.
okay.
This is the real world.
No, this is all right. In generating function world, you're okay. So
Plus,
this-
we did statistics for hundreds of years, and then someone had to make it formal, and
Yeah.
nothing really changed.
right. Well, Gödel's theorem, right? I mean,
Yeah,
you know,
yeah.
they're like, pretend I never heard that. It doesn't really matter. Yeah. So look, it's okay. It's okay. It's okay. Told you it's okay. So it's not an integral or anything. It's not quite as bad as that. Maybe that would be worse.
Actually, integrals are nicer.
Oh, okay.
Especially
That's what we're going.
if one way could be tricky term-wise. I just studied all of it.
Okay. All right. All right.
Super annoying. It's the worst subject ever. Proceed.
Yes. Thank you. So we have almost the generating function for the straight out degree distribution. We have to subtract off the probability of getting 0, which makes sense because that's not really in this guy, right? You never find someone with no friends if you're running along an edge. They are not there. Okay, so we're going to subtract that off, but we have a nice derivative sitting here, so that can get whacked, to use the New Jersey term. Yeah, you're giving it to me. I'm going to, right. So 1 of the average degree derivative of this guy. So that's very nice. Even better, average degree is what in terms of generating functions? No, what do we use? What is it in generating function world now? We've just derived it as a funny little thing. Yeah. The first derivative, right? It's the first derivative, right? So it's the first derivative of the generating function for p, evaluate at 1. So, very nice. Yeah, lovely. See, it's very pretty, right? Opaque, yet beautiful. Okay, very good. This is why the prime thing gets so much play, you know, it's because no one understands what's going on, but it's like, oh. Well, there's also cryptography, but you know. So if you set x equal to 1, that's nice, right? This is an immediate thing that should happen, right? So x equals 1, normalization. That's the probably add up to 1. So that's true, right? So you set it equal to 1. We don't care what the p is. It's fine. That cancels to 1. So that's healthy. Now we're just going to take a derivative of that. All right, let's go back to what our game was. We said that the average number of other friends, if that's greater than 1, and we know now in generating function speak that that's the first derivative, evaluate at 1. So we can do that to our new friend here. This is just a constant on the bottom. Differentiate this guy. So it's the second derivative. And yeah, so there it is, right? So we differentiate it and set x equal to 1. This becomes the average number of other friends that a random node has, and that's our condition. So much clearer. And if you, it is what we, if you think about how these derivatives work a little bit, you know on the bottom that that's the average degree because you're differentiating inside, you get a k comes down. You differentiate twice, you get k minus 1. So really this is the average of k minus 1 divided by the average of k, which is what we had before, right? So this is the second moment squared minus the first moment. Okay, so that was kind of cool. Super cool. Yeah? Mathematics. All right. All right, so it was a bonanza with generating functions, you know, when people kind of figured out they could do these things. Okay, so let's talk about this. How are we doing? We're going to get to, yeah. All right. Now we have to go bananas, okay? So we want the size of the largest component. This is this thing that we did badly before. And we're going to have to look at some new probability distributions. There are also functions of integers, just like our degree distributions. But now we're going to talk about components, right? So this is little pi n, so probably the random node. So we're going to grab a node by its ears, and then it's probably that node belongs to a component of size n. Right? And then we want attached to that, so this is P and R, right, in Greek. So there's an analogy to the degree distributions. Right? So big P was degree distribution, big R was the edge degree distribution. This is a size distribution, component size distribution, so that they were local things. This is a global thing, potentially. Non-local at least. So rho n is probably that you jump on an edge, you run along it. It's probably that leads to these are finite. This is true. There's finite subcomponents. This is an important thing. They're finite subcomponents. So this is now a little bit different. I'll have some pictures. You're running along here. You find a node, and it belongs to some finite component, right, of size n. Now, it's part of some bigger component because there's at least this one node here. But we're just what's out here. Crucial sneaky thing here is we're talking only about finite components. So we're actually going to look at our network, and it's got all these little finite ones around it, which is sort of similar in that wrong calculation, right? We looked at the stuff outside the giant component. We're going to find out all sorts of things about these guys and then say something about this. And because these are finite and it's random, there will be none of this business, right? There's no little circles in here, no little cycles. Okay? No friends. Nothing social. So these are little pure branching things, and that, the math is so much more fun, okay? But this is really nice. Okay, so as I said, so local, global connection. These are the local guys. This is the global stuff here. But they're tied to a node. You jump on a node, look at its degree, or an edge. You jump on an edge, you look at the degree of that guy at the end on the going out. Jump on a node and you look at it, the component's part of, and this is the component that it's part of, right, going out. So we don't include infinite ones. That would be bad, because then we'd have x to the infinity times some finite probability. So we're just going to pretend that doesn't exist. So now we're going to have something where actually we'll have, instead of, right, we've had this, f1 equals 1. You can certainly have f1 equals, you can have this. Right? It could be the generating function for, I don't know, like getting a 1 or a 2 on a die or something like that. Like sort of, right? So that's it doesn't add up to 1. It adds up to something less than 1. And that's exactly going to be our story, because, or the thing we go for, because the probability that you're not in a finite subcomponent, finite component, is the probability that you're in the giant component. Okay. Pictures. Yes. Like this resolution is so much better. Okay, so, right, this is our local thing here. So this is, sorry.
That's a global thing.
Yeah, so it's part of n nodes, sorry, pi n, and this is about edges. Yeah. So we stick these two guys together. Okay, that's right. Okay, so this is pi of n. This is probably, you just jump on this guy, it's probably that it is part of a component of size n, finite. We have this piece. So we take these two guys and we build up one layer out. So these things have to be connected to each other. So we're going to say, all right, what if we jump on this one and we figure out, it's got some degree, right? So we sample, right? We sample from p sub k. And then we sample from these subcomponents coming out of it, and we're using the rho distribution. So this guy plus this guy plus this guy plus this guy plus this one has to equal this, is the story. And so we're going to use, so it's random. We can use this one step of recursion, which we use that little terrible delta equals pk times delta to the n, right? That was very naughty. But we use that one step of recursion, our knowledge of randomness, that doesn't matter what's outside it. There has to be a consistency, right? So this picture should be replicated by this picture. We should be able to determine the probability of finding choosing a node and finding a component, being part of a component of size n, by building up from this, by saying, oh, it has k friends, and then let's sample from this other distribution. Okay. Now, the problem remains that you have to understand. So we know what P of k is, and we know what R of k is, right? Those two are connected. We know what they are. We need to figure out what these rows are and what these pi's are. This one just gives you a connection from the rows back to the pi's. So if we know what the rows are, we know what the pi's are. How's that feel? Nauseatingly silly? Yeah? Right, so this is it's a Markov problem if you like, but it connects pi n, rho n, and pk. We don't have our R sub k in here yet. So that becomes the, this is the important, this is, as I've said before, edges are the big deal, right? So this is where everything happens, and then we go back to the other picture and fill in the details. This is where we actually solve things. So, okay, so we're on an edge. Rho of n is the probability that leads to n nodes. You know, this is one node, you definitely get to one, and then it's going to have n minus one other friends in this finite subcomponent. We're going to use this, which is the this thing, which we know exactly what this is. It's a probability that there are k outgoing edges from the node that you reach, to build up a recursion for rho of n. So rho of n is here. And it has an rk associated with it, right? So this guy gets to here, and we have k friends. Each one of them has, so this is rho of n1, rho of n2, rho of n3, round to rho of nk. This guy, so n1 plus n2 plus n3 plus nk plus 1 has to equal n. So we have to think about all the possible ways this could happen, right? So say this is 73. Well, it could be that you hit, this guy has one friend who's then got 72 friends out here. Or it could be that they have 17 friends, and there are also the possible ways of partitioning 72. So it becomes about partitioning and probability, which seems horrific. That seems pretty bad. Yeah, right? So again, 73 nodes out here. We go one step further. We just sort of break it out one little bit. Like, we don't need to know what all the details of these structures are. What we should have is self-consistency. If this thing works, we should be able to say that just this rho n by itself can be made up of these other little rho n1s, n2s, n3s. And the connective tissue is at this level, which is local, and it's the RK is the connective piece. So it should bind those component stories together. Once we have the rho n's, then we can say, okay, I'm going to jump on this one. I'm going to sample. I'm going to say it's got, a degree k. And I'm going to figure out what's the probability that it can actually, that a node of degree k can actually produce or be part of a subcomponent or a finite component of size n. Right? It might have one friend, and there are all these ways of that one friend. Well, so one friend, and then that has to have. If this is again 112, this would has to be 111. That's probably it has 111. And certainly if it has no friends, then there's 0 ways of doing it, right? So you can sort of see how it's going to work. If this is of size 3, the whole thing is of size 3. Let's say it's size 4, includes 3 others and you in the middle. Then there'll be no way of doing it if this one has 5 friends, right? So there should be a lot of natural things working. This is really, you can read papers and it's not very clear. I'm trying to make it clear. You have to look at this a few times, but these pictures are good pictures. Okay.
So when you say like someone has 73 friends, or this leads to 73 people,
this picture, right?
you're just looking at, so say in that middle node, that connects to,
Yeah.
yeah.
Mm-hmm.
Say that guy has 73, connects to 73 nodes at some point.
Out here, there's a sub, yeah.
Is that just as far as you want to go? As far as possibly can?
Yeah, well, so you look at essentially what you're going to do is look across the whole network and find how many ways you can get that structure of 73. So there are all kinds of little branchings that do it. Some are more common than others. There'll be a very rare configuration, say, where this person has 73 friends, not all of whom have no other friends. You know, and in a big enough network, you'll maybe get that, right? But I mean, you can actually calculate the probability for it. It's low. But that's what we're going to do. We're going to sort of essentially consider all the possible combinations, or all the possible structures, and assign probabilities to them, and thereby get a probability for the whole thing.
So it could just be like a bunch of people having one friend,
Mhm.
70.
It could be so they have two friends, right? Yeah, it could be just a tendril, right? Yeah. So it'll be very rare.
Okay.
No, but you're right.
I'm just trying to think about.
There's a finite probability. There is a probability attached to that. Yeah, yeah. But when you go to this picture, you don't need to see the details of this. It's just a recursion relation. We want to build this guy. So think of this as this little lollipop, right? We're going to say this lollipop has a little lollipop structure inside it. All of these have the same thing inside as well. But we just need to do it one layer, and that will be enough to tell us about, because right, the rows are connected to this row through R sub k. So it's the structure of this thing that's going to is going to help us at least put together an equation for the, No? Okay, sorry. Okay, so let's see. It's delicious, but I guess we're not going to get through all of it. Okay, good. That's the picture. You're going to have to come back to that one. But generating functions, as we've said, we'll construct them the same way for these new probability distributions, right? So f of pi, so for the pi distribution, has exactly the same kind of form. F of rho has the same form. So again, this is a probability that an edge leads to a finite subcomponent of size n. This is a probability that a node is a part of a finite component of size n. Okay. So as I said, I mentioned this before, it's finite, right? We're talking about finiteness. So this is a probability, f of pi of 1 isn't 1. We've said that it is for normal probability distributions, but there's a restriction on the things that can go into this, and we want only the finite ones. So therefore, it's taken as a whole, it's a probability that our node is part of a finite subcomponent, or component, sorry. Therefore, the size of the largest one is 1 minus whatever that probability is. Totally sensible, right? Okay? So before we had a little delta here, now we have this, it's coming from a generating function. It's a much bigger, richer, crazy machine. They're crazy machines, that's what we are. So, the mission is to figure out these things. Now, we know we've done this, right? If someone gives you p sub k, the degree distribution, you can compute these little beasts, right? This one is just, by definition, what it is. This one we now know is the second derivative of this guy. The first derivative of this guy divided by the same thing evaluated at 1. Completely reasonable. So we have those two. And now we have to stretch out and get these ones. Or at least find out things about them, right? So, okay, I'm going to tell you, I'll show you a couple of results that matter. And I think we'll have to reconvene in a few weeks. But yeah, let's try and get these across, and we'll recapitulate these. Okay. Right, two random variables, u and v. They can take on these values 0, 1, 2, right? And so their probability distributions are going to be, so these are, this is like p of k, right? So this is u of k, v of k, or r of k. And their generating functions are going to be fu and fv, right? Fine. So these are sneaky results. If you have this, so say we sum, so this is a funny looking thing, right? I equals 1 to u. So we're going to randomly sample from the u distribution. Okay, so we're going to sample from the u distribution. Let's say it's Poisson. We sample from that. We get some number. It's 7. And then we say, okay, now we go to this guy, and we sample from it 7 times and add them together. So this is, wow, the disdain. This is exactly this story. right? Because R of k is going to say, oh, you have k other friends. Now you need to go to this row distribution and sample from it k times and add all those guys up. That's really what's happening there. So this is a clean version of it. It's pretty crazy. Let me just hold on one second. This is, yeah. So this is a funny thing to. So a classic thing, say in probability when you combine distributions is I've got distribution x of a random variable x, random variable y, z equals x plus y. So what's the distribution of z? And that's a convolution, right? So, that's a natural thing to do. Yeah. You're randomly sampling from this one and from this one, and for some reason you're adding them together. Here, you're randomly sampling from the same distribution repeatedly a random number of times. So imagine this is rolling a die, right? So you could roll a die. You get 1, 2, 3, 4, 5, 6, and you get a 5, and that says now sample from, maybe you roll another die, right? So you roll another one 5 times and add them all up. And that's your thing. So what's the distribution? What's that distribution? Yeah, so for example, that's the question then. What is, you know what the distribution for rolling a die is, very simple, but now we've got this other thing. So there was a I don't know if it's still done, there was a race at CMU years ago where they brought out a huge comedic giant die and rolled it, and that was the number of laps you had to run. So on a 400 track, so 1 to 6. And then I think as the first person came to the end of whatever that was, they would roll it again. So you could get, 6 plus 6, could be 1 plus 1, but you have to figure out, do you burn yourself out? Like you could, because, you might be in front and then it's just a 1, so you just 1. Anyway, sorry. A strong geek word. Okay, so that's a funny looking thing. This is a funny contraption, but this is the generating function for it. This is the generating function for this guy. It's not a composite, yes. Oh, I'm sorry. Yes, this means distributed, distributed as. So this might be, normal distribution. Just generally speaking for statistics. Distributed as a uniform distribution, distributed as a Poisson would be a nice thing for us, or a Power. Yeah. So each one of these has the same distribution. That's the idea here. So it could be the die, for example. Each one is distributed as a die. But we have to give them separate, to write this notation, you have to call them separate beasts. They're separate instances of the same thing. Is that okay? What's going on? The die thing is a lot of fun. Yeah. So in fact, the die thing, let's see. So what we did with the coin guy was, this is just a taste. Let's do this. So a half, 1 plus x. So this was 0 equals a head and 1 equals a tail. So we can turn it into a number counting thing, right? So if we flip the coin and we get a head, that means we get 0. There are 0 things we do, right? But if we flip a coin, we get a tail, then we get 1 sample. We're allowed to do 1 sample. That's if we compose this with itself. So the generating function for the whole thing would be 1 plus, and then so this is f of x. This is a coin. And then you bung the whole thing inside itself. Did I get that right? Right, so this would be composed with itself. So this is a half plus a quarter x. Right, so it's 3/4 times x to the 0 plus a quarter x to the 1. So 3/4 of the time you'd end up with 0, and a quarter of the time you get 1. So that makes sense, right? Half the time you don't count anything up. The other half of the time you get to flip another coin, and you get a 1 for a tail. So that's right. So you could do, what's that? So you could do, a die roll and then a coin, right? So you could do your coin could have 0 and 1 written on it. You do a die roll. So if it was that, you'd put this guy inside the 1/6 x plus x squared plus x cubed. You put that in, So it's pretty nasty, right? It looked like, well, you want to be a little, yeah. So you get a half 1 plus x to the j. There's a 6th, right? This is for coins. The whole thing is j equals 1 to 6. Yeah. That would be the generating function for rolling a die and then flipping coins that have 0 or 1s on them, 0 and 1, and then adding them up. So you 5, you roll 5, and then you flip the coin 5 times, add up the number of 1s you get. But actually a real thing, right? So this is kind of an odd combination of two distributions, it seems like. But very nicely it's this. Okay, so I think the best thing will be, I've just given you a little bit of a start on that. That's we can derive this properly. You can see it's kind of, it's not for right now. I'll tell you another, I'll give you another sneaky little result we'll come to later, just as a, so you can think about this when you're skiing. So v equals u plus 1. So that's very simple. We're just adding 1 to it. You have a random variable, right? So you roll your die and you add 1 to it. That's it. Then you get, that's a very simple thing. The generating function for your modified one is just x times that guy. So we can, that's not bad. And then I think there's a generalization. Yeah, and so we'll get, and that will all allow us, that's all we need to go back and sort all of this out. So much happiness. It's fun. It's totally fun. Totally fun. And yeah, crazy. All right. So good. So you have a couple of assignments. Not about this. It will be about this soon. But yeah. All right, people. Great. So that was fun. So what do you think? Doable? Yeah. Painful? Bring your V8 with your caffeine. More food? I'll bring more food, Nick. Okay. So like 5 times as much as that? I'm serious. How much do you need? There's none left, right?
Probably not.
That kept me going pretty good.
All right. Well, I'll bring it out halfway through as well, I guess.
Yeah. We can bring our own food.
No, I can bring out,
Yeah.
sneak it out.
Restock us.
People are looking tired. I was like, all right.